Ladies and gentlemen, good evening, and welcome again to the scheduled session of today. That's not our normal session as we used to, but normally I will ask for you to kindly hint to me to say I'm audible enough, so that I know that you can all hear me, and at the very same time ensure that I can hear you as well. So maybe without wasting any time, if one can be able to maybe give a text message or someone just say hi to me so that I can hear that I'm also audible enough and you guys can be able to hear me as well before we can start the session of today. Anyone?
Good day, sir.
Thank you very
Good
much.
evening.
No, it's good evening. Thank you very much. Without wasting any time, thank you, Manuku. Thank you, Tiamo. So without wasting any time, guys, we are scheduled now to start with electrostatics. This is now what we should be start talking about, and it's one of the topics now that has a great impact in terms of paper one. So basically what it says is we'll be moving with this one from grade 11 also to grade 12. So it says now basically this is now a very, very important topic to look into. So I'm going to come up with few smaller strategies as to how best can we be able to ensure that we understand and we don't leave any basic gaps when we move forward with electrostatics. So first things first, I'm going to start now at the center where I have the topic itself as electrostatic. But what is it that I need now to know from electrostatics? The very first thing to know is what we call charge quantization. So this is the first thing that I need to know. Thereafter, I will need now at number 2 to know what is known as charge transferred. Charge transferred. Thereafter, link it now with number of electrons. And then after number of electrons, we obviously have rules now that governs everything that we do in specific topics. So we will now link all this with what we call Coulomb's law. Coulomb's law. And then thereafter, further extend it now to what we call an electric field strength. So all this are key concepts and key knowledge areas that each and every one of us should be able now to understand in detail, because it's what governs now the section of electrostatics. But now I'm going to try and take each one of them slowly as we move. So in this same sequence, I'm going to try now and move with what is charge quantization, what is now charge transfer, and how can we calculate for charge transfer, how best can we calculate the number of electrons, how best can we use Coulomb's law, and finally reach a point where we talk now of electric field strength. So now let me get a page and now start with charge quantization. So for charge quantization, we focus now on a new charge formed the charges were in contact with each other. So it says now, for me to fully explain, the key thing is the charges must be in contact with each other. So if the charges did not now become in contact, if they did not touch, maybe I should also add here to say it's important that now if they are in contact, it basically means they should also touch. So if they did not touch, it means I cannot talk of charge quantization. If they were never in contact, then I will not be in a position of talking charge quantization. But now check here. We also say we are going to have a new charge. We are going to have a new charge. So what it basically says when I have a new charge is that I am going now to have two spheres or two charges that were in contact. But now because of them being in contact, I am now going to have two charges now with the same charge. So let's make it a simple thing of saying, if this is the case, for me to calculate my charge nu, for me to calculate my Q nu, now remember, Q nu is the new charge after the spheres have touched or the charges have touched. So it is going to be Q1 plus Q2 divided now by 2. So what does this say? It says now, if I have a charge here, which is a plus 6 coulombs, if I have a charge here, which is now a plus 6 coulombs, and I have another charge here, which is a minus 2 coulombs, and then we are in a position that now somehow they touched at a particular instance. So once they've touched, it means I'm going to have a new charge here and a new charge there. That is what it's basically saying. But now they only be a possibility of a new charge if now the charges did now what? Did become in contact with each other, did come in contact with each other. So I'm going to use this already as an example. I'm going to have a 6 minus, plus minus 2 over 2, which will be now 6 minus 2, it's 4, and then divided by 2, I'm going to have a plus 2 charge, 2 coulombs for that matter. So what it basically says is, I am going to have this now 6 coulombs charge as a 2 coulombs, and I am going now to have this one also as a new charge of 2 coulombs. So what it basically says, after they have touched now and separated to its original positions, then we are going to have a new charge in each sphere. That is where now most of us will make a mistake. Remember, in each sphere now, we are going to have a new different charge. So this is what we call charge quantization. So charge quantization is basically now formed after the charges were in contact with each other. So I need now to have two charges for this particular concept to take place. So I hope it's clear. Just bear in mind that you need now to consider the charges, because now the charges in electrostatics, they influence our final answers, especially in charge quantization. That's the reason why I substituted now my 2 charge coulomb as a minus 2. So for that, it means now I'm allowing to have the average of the two charges that now have been uh, have been in contact with each other. So by so doing, I will be able to get the average thereof. I hope everything is still clear. So I will just move to the other section, which is now number 2. Let me add the page for that. And then adding a page for that, we go to charge now transfer. So at 2, charge transferred. Charge transferred. So now with charge transferred, what we basically say, the two charges must be in contact with each other. But after being in contact, obviously we can see that there is another one that lost the charges and the other one gained the charges. But charge quantization basically said, remember, after the spheres have touched, we now get now an average of the two. But now with charge transfer, we are focusing now on one sphere that has either gained electrons charges, or one sphere that has already maybe lost charges. So what we need to do in this instance is for us to be able to generate a general formula, of which is not part of the formula sheet. What we usually say is charge transferred equals to charge after contact. That's now Q, charge after contact, minus now charge initial or before contact. Charge initial before contact. So if this is the case, it basically says to me now, if I go back and look maybe and assign A and B, and then I still have A and B. So working with B only, I should write it here, focusing on B only, or charge B. It basically says, what was our initial charge? Okay, let's look for A will be a nice example to do, focusing on A. So we want to know the charge that was transferred. And remember, I did say that now this you will not get in a formula sheet. So kindly write it down. So what it says is, when we are focusing on A, remember our A was a 6 Coulomb charge. Thereafter, we got now an average of 2 after the contact. So what does this say to us? It says now we are going to have a situation where we have is equals to the charge after contact was a +2. So we are going to have a +2 minus now the initial charge, which was 6. And then now -4 is our answer. And then we conclude to say our final answer is 4 coulombs. But can we basically be in a position of explaining what this answer says? Remember, the answer now is a negative answer. So it basically says, when you look at these two, we usually say electrons only now, or charge moves from negative to positive. So in this case, it basically says we need now to consider the charge we did, which is now minus minus, and then we are now after contact have 2, and now initially we had a plus 6. So this allows us to be in a position of saying we are now going to use the charges that we received, and now we are going to get 4 coulombs. When you look at it now, it doesn't make much of sense, because now we anticipate that you should not be losing charge, or charge will not be transferred between now the two charges. But if this is the case, then you should be in a position to do it the right way. I'm just going to check for the hands. I saw there are a few hands that are coming in. I have Obaging. Obaging, the platform is yours.
Okay, can you hear me?
I can hear you fully, sir.
Okay. So I wanted to ask, if the answer was positive, what does that mean?
Okay. If now the answer is positive, ne? It basically says
Yes.
we lost the charge. If the answer is negative, we are gaining the charge. Remember, the charge only moves now from negative to positive. So if the answer is positive, it basically says we lost now the charges. But if it's more negative, it basically says we've gained more of the charge, so we are becoming more negative. So more negative basically means gaining, and more positive basically says losing. Hence now the new charge quantization. Remember quantization, I said we are forming now a new charge. That is the reason why we end up now with this kind of answers. Yes, sir. Thank you very much.
I can.
Thank you very much, Monghadi Tsiamo. So that is now the formula. Remember, guys, it's not in the formula sheet. So, but I will share the slides as usual, so you will be able to get it. You can use it now in all the informations that are given to you. Then the third one, at a page. The third one, we said it should be now number of electrons. Okay, it's number of electrons. So number of electrons. Okay, I see Ntabi saying your hand is up, and Ntabi saying Shabalala.
That I was asking if should we specify on whether we gained a charge or we lost a charge on the charge transferred.
It's not. Okay, it's not important. Ne? The basic thing that we expect you to know is when to use a minus, when to use a plus, and basically how do you calculate the charge transferred. We don't necessarily need you to specify that this one is gaining, this one it's losing, because what is going to happen, you'll always get an answer that is negative and an answer that is positive, but it should be the same magnitude. Ne? So if it becomes the same magnitude, then it's when you need to be in a position of explaining. So if it's positive, basically it just says you are losing electrons, and then if it's negative, it basically says you are gaining more charge. So we don't need to specify, but at some stage, maybe for the purpose of closing all the gaps, maybe if we are in a position of explaining, then we will be doing the right thing. So for me, I would just say it's not so needed, because we are just looking at the value or the quantity of how much charge was transferred or how much charge was lost thereof.
Okay, thank you, sir.
Thank you very much, Ntabisi. Now, number of electrons, it's very clear and straightforward. And there's a formula that we use, is N, which is Q now over QE. Where Q, SA2, kindly mute yourself. Thank you. So now with number of electrons, we look at the formula that is given to us. So with the formula, we are in a position of say this now will be your charge, and it must be in coulombs, and this here will be your charge of an electron. Charge of an electron. But now this charge of an electron, we get it in our formula sheet. It's a constant, and it's a constant that all of us should be able to know. So it is something like minus 1,6 multiplied by 10 to negative 19 coulombs. 19 coulombs. So be on the lookout that everything here should be in coulombs. Your charge should be in coulombs. Your charge of an electron should also be in coulombs, such that coulomb and coulomb can cancel, and then we just get now a number for or the number of electrons thereof. So for us to be in a position of doing that, it will also be easy, because now we are going to look at now only one specific charge. Hence, I said with now here we are focusing on A. Remember A, it's this one of 6 before touching, and then 2 after touching. So it basically says, if you are focusing again on A, I am going now to use my 6 coulombs divided. Now this is before contact, so I must maybe focus after contact. So focusing after contact, it means this must be 2 divided now by minus 1 multiplied by 10 to negative 19. Negative 19 coulombs. And then you get your final answer. Let me get my calculator quickly. So my calculator says it is 2 divided by 1,6 exponent negative 19. So the answer is 1.5, 1,25 multiplied by 10 to the power 19. 1,25 multiplied by 10 to negative 19. So we write it down, 1,25 multiplied by 10 to negative 19. Now, somebody will ask me, but it's not possible to get a negative answer for the electrons. To say I have negative 1,25 to power 19 electrons, that is not the right sign. So it basically says now the minus we can easily ignore when substituting into this particular equation, because every time now if we substitute and then we get a negative answer, it doesn't scientifically say anything with us, unless if now I was focusing on a specific sphere that is now a negative sphere. So if it's a negative sphere, then I will be in a position of saying, then I can substitute with the negative. So it will be negative, negative, then it will still give me positive. There is no way you can be able to say you have negative 1,3 electrons. It's like saying you have negative 4 eggs. That is not possible. So my point is, depending on the charge that we are working with, we can easily be in a position of substituting with the negative or substituting now without the negative. And I must now show you that basically we don't need to have the negative. So it's 1,6 6 multiplied by 10 to negative 19. Then it will give us now a clear understanding. It will give us now a clear information of saying this is the number of electrons we have. I think I saw a hand up. Manuku, your hand was up, or are you covered?
Nasta, you rectified your mistake, so it's fine.
Okay, thank you very much. So now, the question should be, okay, Hope.
Sir.
Yes, sir.
Good evening. I was saying, okay, I understand that the value shouldn't be negative, but what about the exponent? Because my calculator says the 19 is positive.
It's positive. Nope, I have to beg and differ with you, because now for an electron, I have it now here under the constant as 1,6 multiplied by 10 to negative 19. So it's either you are using a wrong data sheet, but it should be negative 19, say. So kindly verify the data that you have or the formula sheet that you are using.
Okay, sir, I'm going to look into it.
Thank you very much, Hope. But it is negative 1.6 multiplied by 10 to negative 3. Mr. Marshall Villagaz.
Yes, sir. Good day.
Good day, sir.
Referring to what you were saying that the number of electrons cannot be a negative. So when it comes to putting it in a calculator, because like physically speaking, truly speaking, I did exactly what like you were saying here, and I made the charge of the electron negative, and my 19 is positive, like Hope says. So
The
how
final
do we
answer.
get it?
Or the final
Yeah,
answer, not the constant. Okay, let me
the
take
final
my
answer should be
the
positive.
final answer. Okay, I was thinking Hope was
The
saying
final answer.
okay, no, let me
These
have
are
my
the questions.
calculator again. Okay, 2
No.
divided now by 1.6 exponent negative 19, then it must be positive. The final answer,
Exactly.
not the constant.
Exactly.
Okay, no, I hear you now. Thank you very much, gentlemen.
Thanks, sir.
No, 100%. It must be positive, but not the constant. No, the constant remains 1.6 multiplied by 10 to negative 19. Thank you. Now, we move to the number of electrons. Okay, that one is done. And then the fourth one now will be Coulomb's law. And this is what Coulomb's law says. Coulomb's law says the magnitude of an electrostatic force exerted by 1 point charge on another point is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. I'm going to highlight few words as we move, as the magnitude of the electrostatic force exerted by a 1 point charge on another. So what it basically says is I need now to have charge 1 and charge 2. So I'm just going to call this one Q1, and then I'm going to call this one Q2. It says now it's directly proportional to the product of the magnitude of the charges. So from that, it says now F is basically directly proportional to Q1 and Q. The product, remember, says it should be the multiplication between the two. But now, and inversely proportional to the square of the distance between them. And then it means there should be a certain distance between the two spheres. So what does this basically say? It says now F should be inversely proportional to r squared, which is now the distance between the centers of the two spheres we have. So this was now taken in such a way that we generate one general formula. So the general formula for Coulomb's law is basically F is equals to K Q1 Q2 over squared. But now where does K come from? K is what we call proportionality constant. So proportionality constant, proportionality constant. So proportionality constant, or this K for that matter, it basically now normalize this lot of English that is being said here. So because of once we refer to the other one being directly proportional, the other one being inversely proportional, it basically says to me, fine, then I need to have a proportionality constant. So with this proportionality constant, it's what normalizes or allows me to have the equal sign here. So I will never talk of equals to if I do not have the proportionality constant. So the proportionality constant is there to allow us to write these two statements in terms of the equal sign. So the equal sign comes after having now to have a proportionality constant. So this is a basic law that each and every one of us must be able to know. This is a basic law that now is going to govern a majority of things when we move forward. But now, does it necessarily say, is it possible for me to take this information and write a general formula in terms of the graphs? Yes, I should be in a position to do so, because the mathematics allows me to have, okay, let's copy this and delete the sketch for us to have space. Okay, let's have another one moving like that. Fine. Then we can be able to say, but now what if I am in a situation of drawing F versus now the product of Q1 and Q2? So it basically says I will have my F. I will also have the product of Q1 and Q2. So I intend on drawing a graph for this situation. But what does the law say? The law says now, if I have the product of Q1 and Q2, it should be directly proportional to the magnitude of the force. If I have now the force and comparing it with now the product of the two charges, they must be directly proportional. So directly proportional basically means they will increase with now what? The same amount or the same magnitude throughout. So this will allow me to have a line that starts here at the origin and move constantly throughout. So this will be now my first graph that I am going to get, because of now the directly proportional. So the increments should be now the same throughout. So allow me to duplicate this. Allow me to duplicate this. And then now I can remove and create more space. Fine. Now I'm going to try and draw the one of inversely proportional with r squared. So the one of r squared, remember, because of the proportionality constant, if we draw 1 over r squared, it should also be a straight line thereof. But if I draw f over r, r squared will now allow me to see exactly how r influences the magnitude of the force. So in a situation of having my axis, and I should specify that I am drawing now for f versus r squared, not 1 over r. Because if it becomes 1 over r, then we are going to get now a straight line because of the proportionality constant, and now having to take the inverse thereof. So if this is f, and now this is r squared, it basically says I am going to have a shape which is somehow of this nature. I must just turn it around. And then this should be my f, 100%. Then can I be in a position of taking the inverse? If I do take the inverse, then it's important for me to highlight that I am still going to have the same axis, and I'm still going to get my straight line. But now, what is the name of this particular graph? It is going to be a graph of f versus now 1 over r squared. So if I have 1 over r squared and then I have f, I will get now a straight line. So this is because of taking the inverse thereof. So these are the 3 important graphs that each and every one of us should be able to say something related to them. Because in an exam, there are high chances lately of us now exposing you to the graphs. So exposing you to the graphs is we expect you to be in a position of being able to answer, being able now to perform calculations that are fully based on the graphs. You will usually get this type of questions either as a multiple type of a question, or even in a position of explaining or interpreting the graph that is given thereof. So I'm going to further move on from this slide, and then maybe I should have a nice clean page. So with a nice clean page, what I intend on doing is I want us to go back a little bit to what we know as Newton's third law. So at number 4, I want us now to say something about Newton's law. Quickly, anyone who can just state Newton's third law for us? Anyone, quickly? Newton's third law?
Newton's third law is when an object exerts a force on object B, and object B simultaneously exerts an oppositely directed force of equal magnitude on object A. So it's also called an action-reaction pair.
Okay, simple English. Thank you very much. Have you saying action, reaction? I believe most of us should understand that. It's very, very key. So it basically says when body A exerts a force on body B exerts the same amount of force, but in an opposite direction. So where am I taking this? I am taking this to a point that now I have Q1 and I have Q2. But now Q1 is positive and Q2 is also positive. So the question that comes thereafter is to say, draw a free body diagram, draw a free body diagram for all forces acting on each sphere. That is very, very important. Now we must draw a free body diagram. Now remember, what did we say? We said because we are working with forces and a force which is now a vector quantity, we should be in a position of giving either direction or being in a position of explaining either in terms of attraction or repulsion. So I'm going to add few things here for the purpose of highlight. So if I have, let me use red. If I have now unlike charges, we expect to have attraction. If I have now like charges, I am going to have now what? Repulsion. But what does this mean? Attraction basically says they are going to move towards each other. Repulsion basically says they are going to move away from each other. We need to emphasize that. But with what? With the same amount of magnitude thereof. It will only be influenced if we start considering it will only start now being influenced, or the magnitude of that particular free body diagram that I'm drawing will only be influenced once I start now changing the magnitude of the magnitude of, once I start now changing the magnitude of the distance between the two. As long as the distance is the same throughout, then it means what? It means I am still going to experience the same force thereof. So remember, when they move now, it will be because of Newton's third law. But once they are in contact, once now we have a position where our distance is not the same, then it's going to influence our magnitude of the force. So we need to be in a position also to say, can we draw the correct free body diagram? Yes, we should. And this is where most people do a mistake. So because of we have like charges here, which is Q1 and Q2, both positively charged. If I am going to draw now my free body diagram for each one of them, I must consider which force is applying a force on which particular object. It cannot be that Q2 applies a force on itself. It cannot be possible. Because for me to apply a force, like you guys said, action, reaction, it means there has to be an opposite force coming from another side. There has to be an opposite force also coming from another side. So in this fashion, it says now, there's no way I can say Q1 is exerting a force on its own. Q2, it's exerting a force on its own. No, now the language starts changing. The language starts changing to say which force is exerting of which charge is exerting a force on which specific charge. So we need to be in a position of explaining fully. We need now to be in a position of labeling our forces correctly. So if this is Q1, and this is Q2. It basically says now Q2 because they are pushing away or moving away from each other because of repulsion as well as them being like charges. So what do I expect? I expect now that I will have a force in this direction, and this force will be now force of Q1 on Q2. That is very, very important. I will have now another force in this direction, and this force is Q2 on Q1. So hence I said there is no way Q1 can apply a force on its own. So Q1 is just our reference charge, Q1. And then Q2 also is other reference charge that we have. This we are going to need when we start now moving into more complex problems. This we are going to need once we start now looking into what will happen if I have now two or more charges to consider. Because with this, it's easy to perform calculations. With this, it's easy for us to understand the number of charges, electrons, and everything that are going to be dissipated, or the ones that are going to be lost. But it's key for us now to be in a position of saying, if this is the case, can I do it now for attraction as well? If I want to do it for attraction, it means I must be in a position of saying, if I have now positive Q1 at a certain distance with a negative Q2, will I still be in a position to draw a free body diagram? Free body diagram of all forces acting on each sphere. Free body diagram of all forces acting on each sphere. But now when you look at it, you find that Q1 is positive, Q2 it's negative. So it means now they are going to start pulling towards each other for the attraction to happen. Because now if I'm starting to move in a different direction, then it basically says the attraction will not happen. So it basically says if I have Q1 and I have Q2, they will start now moving in towards each other. This will be Q2 on Q1, and I will have this one now, which is F of Q1 on Q2. So this is what I want us now to fully understand, because once we introduce the third charge, we will need now to be in a position of explaining exactly which one is our reference charge. I'm going to give you some time for you to digest this. I think a minute will do so that I can understand that all of us, make it 30 seconds, so that all of us are on the right path, on the right page, and then we will be able now to move further on. If you have a question, raise your hand If you have something to say, type it in the chat, then immediately thereafter, we will continue. Thank you very much. I didn't see any hands, so I guess everything is fine. I didn't see anything on the chat, so I believe everything is fine. So let's just move on. Wait. Something just happened to my screen. Let me just share it again. Let me just share it again. Yes. Okay. Okay. I think we can continue. So hence I was explaining, guys, we need now to be in a position of doing this now in detail. So I'm not going to bother you with calculating for the two charges, because once we work with two charges, honestly, it's not going to be in an exam. If it's in an exam, maybe it's a level 1 type of a question. But my key idea is I want us to move now to more complex things. And understanding more complex things, we will build up on the little that we have. So if you check here, we started now with two charges. We also moved now to two charges. I'm interested in now what will happen when I have three charges. So let me add a page and say now, let's look into three charges that are arranged in one dimension. So three charges, okay, I think this is now number 6, if not 5. Let's make it number 6. And then we say three charges. Three charges in one dimension. This is very, very key. So what it basically says is, you now have your three charges, and these three charges are in one dimension. So one dimension means now all charges are aligned in the same direction. So what this basically says, it just says now all charges are placed in one what it basically says. So all charges are placed in one surface, or we can say in one arrangement. So you'll not find now the other one, or basically we can just say they are horizontal. All of them are horizontal or vertical. All spheres are horizontal. All spheres are horizontal. So once I look into the question that is given, and I'm in a position of understanding that now the three charges that I'm working with, they are arranged in one surface, or they have the same arrangement throughout, or all the spheres are horizontal, then it means I can apply now the following. So as hints for how to work with three charges, the first thing is check the reference charge. Check the reference charge. What is a reference charge? A reference charge, where do we get it? This now should be always be given. When you read the question will be specific. Are we working with Q1 or are we working with Q2? Are we working with Q3? So the reference charge should always be given. There is no way you will be able to draw the correct free body diagram if you do not understand or even know which reference charge are you working with. Basically, the reference charge is actually the question. So once we are able to pick it up that now this is the reference charge, then we will be knowing exactly what now to do. Thereafter, at number B, we say after drawing the checking which is the reference charge, draw a free body diagram. Draw a free body diagram. A free body diagram for all forces acting on the reference charge. This is very key. Of all the forces acting on the reference charge. So where is the reference charge? We said the reference charge is the question. The reference charge is now the one that I will be working with. The examiner should be in a position of telling me exactly what is it now that I need to work with. If it's not giving me anything, then it will be impossible for me to know what is it that I am working with. So after drawing a free body diagram, you will need now to calculate the magnitude of each force acting on the reference charge. So basically we are saying use F is equals to K Q1 Q2 over R squared D. But now what does this say? It says to me, once I have three charges as hints of how to approach this, it means now use the equation 2 times, because you will always have now what? A force from sphere 1 and then a force maybe from sphere 2. So basically what it says is we will always be in a position of now having what? A maximum of 2 forces. So maybe as a hint, expect to have a max of 2 forces. A max of two forces. Once you have now what? 3 charges placed now horizontal. Fine. Then calculate the magnitude of each force acting on the reference charge using F is equals to KQ1, Q2 over R squared. Use the equation 2 times. That is key. Why do we need to use it 2 times? Because at the end of it all, the key question will be now what? Calculate F net. And calculating F net, it will always be now F net is equals to F of 1 on 2 or plus minus. It's just A and B. A and B plus minus F of B and A, maybe something like that. So what does this basically say? This basically says, if I know now my direction in terms of the force, I can be able to know which one is a minus, which one is a positive. So by so doing, I will be in a position of calculating the F net. But remember, everything that we did now from slide number 1 to this particular slide, they link with one another. So check the question fully, because at times you'll be expected to draw a free body diagram after they have touched, after they have been in contact. Then we are going to have now what? We are going to have that charge quantization. After then contact, then they can maybe refer you to using the charges that were transferred. So it's important also to check which charges were transferred. So I'm going to try and draw the basic free body diagrams with you together of different charges and different scenarios. But now we will be able to just use the equation, because I don't think all of us will be in a position of not understanding fully. I'm going to allow hands now. I see Mr. Marshall Villagaz, your hand is up.
Yes, sir. I was looking at the calculating the net force in a way, the F net. I realized that you said F net equals to F of AB plus or minus F of BA. But according to my investigations, it's more of net force equals to F of A on B plus or minus F of B of F of C on B. It would seem that B is sort of our reference charge in a way.
Okay, hence I said this is just a generic statement. The questions that follow, yes, the questions or the examples that I'm going to make now, they are going to be specific. Now, remember, I said a reference charge as bullet number 1. Ne? So now we are going to have an example where we clearly know which one is our reference charge. So then it means now this generic statement, the general formula that we are trying to generate, will now be applicable fully.
Okay, so I understand.
Thank you very much, Mr. Villagaz. Let's add a new page. Now let's start with example number 1. And we still have now 3 charges thereof. So I'm going to have Q1. I'm going to try and keep the distance the same, Q2, Q3. So this is 5 millimeters. And then this is also 5 millimeters. And we don't worry about the charge, we quantize it, but I want this one to be positive, this one to be negative, and this one to be positive. And then now they say to me, calculate the net force. Okay, let's make it complex. Yes, calculate the net force acting on Q3, the net force. So can you see now that it basically says if we are going to work with Q3, then the statement is clear, emphasizing that Q3 should be my reference charge. So whatever I am going to do, I am going to draw a free body diagram. The question did not say draw a free body diagram, but check. Even if I say calculate the net force, we are not having the magnitude of each individual forces. So we will not be able to get there. But now I am taking it a step further as a challenge to say, if this was the question, there is no way I can be able to get the net force without drawing the correct free body diagram. So hence, I want us now to go back and say, have we identified our reference charge? Yes, we have, because the instruction is clear that we are working now with Q3. Happy. Then now can we draw a free body diagram of all forces acting on the reference charge and expect to have a maximum of 2 forces. So we are going now to try and draw for Q3. So drawing for Q3, we are just going to say, if I have now Q3, what will be the influence of Q1 on Q3 and the distance thereof? So Q1 and Q3, it's positive, it's repulsion. So if it's repulsion, it basically says this force here, of which is going to be a smaller Yana force, will be force of now Q1 on Q3. I repeat, Q1 is positive. Q3 is also positive. So what is it that I'm expecting? I am expecting repulsion between the two charges. So which force is acting on the reference charge? Which force is influencing now Q3 to become or to repel? It's Q1. So hence now the force of 1 onto 3. So it's going to push it now to the right. But why do I have it with this small magnitude? Because remember, we said now, once we have a bigger distance, where is that now? Should be here. Okay. That part where we spoke of inversely proportional. So now, the smaller the force, the smaller the distance, the bigger the force. So in this case now, the bigger the distance, the smaller the force. That is what we meant with inversely proportional. So, but now I still need to look into what is the influence of Q2 on Q3. So I am going to have now a bigger force, which is now F of 2 on 3. So from this statement, Mr. Villagas, I can clearly see now that the 3 here becomes now my reference charge. I can easily see now that what is the influence in terms of magnitude of 1 into 3. I can easily see now in terms of the magnitude, what is the influence of 2 on 3. So now moving forward, it will be easy for me to decide to say, I am just going to take this particular direction as positive. So when I come to F net, it will be F net now will be F of 1, 3 minus now F of 2, 3. So the generic statement doesn't now sustain. The generic statement does not apply in this particular instance because I am told which is my reference charge. So once I know my reference charge, everything becomes nice, clear, and easy for each and every one of us to fully understand, because now we treat them now as forces, as vectors, so we should be in a position of fully explaining why do we have the negative and why do we have the positive. So 1, 3, because I am told and I am aware of which is my reference charge. So for the very same particular problem, I am going to copy this and now decide to change the signs. Let's change the sign and we make it now example number 2. So with example number 2, the only thing that we are doing, we are now changing the reference charge. I just want to show you with a simple problem that we think we can be able to do. The emphasis is the approach thereof. So once the reference point is changing, then a lot of things will start changing as well. So I want us now to focus on, let's delete this. Let's make Q2 now acting on Q2. So even if we calculate, we are not going to be able to calculate. We are not given any magnitude of the charges, but the emphasis is the approach thereof. So if the approach is fine, then it means we will not be having problems to calculate whatever is given. So we further say Q2 is our reference charge. So what is the influence of Q1 on Q2? But Q1 is positive and Q2 is negative. So I'm expecting attraction between the two. So I'm going to have attraction of Q2 moving towards Q1. So this is F of 1 on 2. And I am going to have almost the same magnitude in terms of F2, 3 on 2. So what does this basically say? It says now because of the magnitude here of the distance, which is 5 millimeters, because of the distance between Q2 and Q3 of 5 millimeters, then I expect to have now the same magnitude in terms of the length of my vectors. So already with this one as well, saying now upward as positive, or sorry, to the right as positive, then it's easy for me to say my F net in this case should be now F of 3, 2 minus now F of 1, 2. Then the generic statement again doesn't hold. So if the generic statement doesn't hold anymore, it basically because of I drew now the correct free body diagram. I'm going to pause and give you some time to digest. And if you have questions, feel free to do so. I didn't get any hands, so I guess and believe everything should be fine. Let's duplicate this one more time to give you another set of a different question that with the very same example, you can just manipulate the system whichever way you want. So I'm going to remove this and make this now example number 3. Make it example number 3. And then let's say we work with all positive charges. And Q2 is still our reference charge. What do we expect to see here now? What do you expect to see acting on Q2? Okay, then this one becomes nice to say I'm going to have my Q2. But what is the influence of Q2 of Q1 on Q2? As plus plus, they must repel. Repulsion basically means Q2 is going to move away from Q1. So smaller than a force. So F of 1 on 2, that is a repulsion force. And now we have the influence of Q3 on Q2. Also repulsion, it basically says Q2 will move now away from Q3. So we are going to have now 3 on 2. Looks like it's the same thing from the previous one we had, but now check how basic a sign can influence now the amount of, or even your free body diagram thereof. Hence, we need now to be in a position of fully understanding how to work with all these particular charges. Because now if I change a sign, it looks like I'm still getting the same thing, but now it can't be the same thing because of the sign thereof. So it basically says I'm still going to have my F net. Taking to the right is positive. That's F of 1, 2 minus now F of 3, 2. I know most of you, when I said calculate, the question was, but how are we going to calculate without having the magnitudes of the charges? Yes, eventually we will get there, but the key idea was now to give you what the hints, the strategy of answering each and every single question thereof. So if you have the strategy, if you understand the science, if you understand the quantization, then I don't think we should be in a problem or in a situation that is now challenging thereof. I want to make one example again where we have now charges moving in, forcing one into a specific direction. I'm going to try and make Q1 a reference in this case. But if I make Q1 a reference, then it means, let me copy. Okay. Now this is example 4, 5. I think it's 5. It's example 5. And then we remove this. And then we make Q1 our reference. Q1, but now I want to change this as well and make it negative. Yeah. Then Q1 is our reference. So Q1. Oh, I can even make it positive. Again, keep it as it is. So now what will be the influence of Q2 on Q1? It's going to be repulsion. So it basically says Q1 will be moving away from Q2. So I'm going to have this force here, which is now F of 2 on 1. I want to make this one bigger for a specific reason. Then I check the influence of Q2, Q3 on Q1. So the influence of Q3 on Q1, it's also repulsion. But because of the distance now I am working with 10 millimeters, the force is going to be small. So I'm going to have another force here, but this force is force of now what? 3 on 1. So can you see that now I have the forces now moving in the same direction? I have now the forces moving in such a way that I am looking at my reference charge. So my reference charge now allows me to be able to know exactly which choice of direction should I use. My reference charge and the free body diagram thereof allows me to know exactly, eventually, I am going to get F net, which is now choosing this direction as positive, which is 3, 1, plus now F of 2, 1. So whatever I do eventually after calculating F of 1, of 3, 1, which will be Q1 and Q3 divided by R squared, as well as F of 2, 1, which is now K Q2, Q1 over R squared, the distance between the two. Once I have all this, it means now I'm in a position of going for the F net. I'm going to allow questions for the next 30 seconds. If there are no questions, then I believe we can talk further. I didn't see any hands, so I believe everybody is fine with this one. So when I check my clock and my watch here, we're left with 5 minutes. So if you don't have any questions, I would just like to say kindly don't rush into understanding the calculations. And I think by now you have seen and you have realized that I'm one person who teaches concepts in detail, and then the questions will follow later. So I'm still going to share the PDF document of this particular presentation. Then after this, when we meet on Wednesday, we'll add 2-3 types of questions and then move a little bit higher in terms of the exam type of questions. Remember when I started, I said this topic is very important because now it also overlaps to grade 12. So it basically says now there is no way we cannot do everything in detail. We must do everything in detail such that each and every one of us understands. So I'm going to share the slides with you or the PDF document and kindly check them through. If there's something that you do not understand, feel free to do so. I didn't want to bother you with the basics of calculating or using F for two charges because I feel that each and every one of us should be capable in doing that. Thereafter, I introduced now another way, which is a nice summary of how best can we go about attending to three charges in one dimension. Wednesday when we meet, we'll add now 2D. That is where things will always be now coming a little bit complex. Hence, I'm saying normalize yourself with this, fully attach yourself now to the hints and understand how we got to drawing the free body diagram. Example 1, example 2, example 3, example 4, and example 5. So I'm going to send the document, and then I think I will also send it with this question. So if you are able or in a position of doing it, I honestly do not have a problem. You can continue ahead doing it, but I will definitely change it for the purpose of the next lesson. I wanted us to look into it, but now because of time, we will not be able to do that because I understand most of you have started now with their exams, so we don't want to keep you for long. So I'm going to send the PDF together with this question. So if you are able to do it, I will be very happy. If you cannot still do it, no problem. I will touch on it when we meet. So last time I'm checking the hands. For the last time, I'm checking the hands. Mr. Marshall Villagazi.
Yes, sir. I was asking concerning the Kahoot test. Will we be doing them this week?
Not this week, because Wednesday is then that I think we will be in a position of finishing this particular chapter. So once the chapter is finished, is then that we can have the Kahoot test.
Okay, sir. I understand.
Okay, thank you very much.
Thank you, sir.
Any other questions, guys? You're so quiet today. What's wrong? Any inputs then, such that I can close the meeting? Okay, now that I see most of you are happy, I believe I was straightforward and concise in terms of what we are doing. So I'm happy that I think you're getting the hang of how I do things, and thank you very much. Also, I can see that the participants are always increasing. So it means basically each and every one of you got their data. So it is exactly 2030. So from me to you guys, thank you very much. Have a good night, and we shall talk again Wednesday, 7 o'clock. Just be on time, so that I always try to open the meeting at 6:30, so that maybe most of you can start logging in, so that 7 o'clock we will be able now to start. I think we are covered. There isn't anything in the chat. So it basically says, guys, that's a good night from me to you, and all the best with your exams, and see you very soon. Thank you. Maybe you should now write few comments in the chat so that I can include them in my report as well. Thank you very much. Have a lovely evening.